Welcome back. Ready to dive back into the world of Irving Langmuir?
Absolutely. Last time we explored his work with tungsten.
Right, right.
But today we're shifting gears
Okay.
to his Nobel Prize-winning research on oil films.
Oil films.
Mhm.
That's a bit of a change of pace, isn't it?
It is, but it's fascinating stuff, trust me. We're essentially getting a glimpse into Langmuir's Nobel Lecture
Oh, wow.
through this lecture series by P.K. Ghosh on innovations in chemical technology.
So it's like a deep dive within a deep dive. So where does this lecture fit in? Like, what's the context?
It picks up right where the last lecture left off.
Right.
It's actually Lecture 9, continuing the discussion on Langmuir's key accomplishments. And the focus, well, it's on his work with oil films on water.
Oil films on water. I have to admit, that doesn't sound as thrilling as, inventing light bulbs.
I know, right? It might not seem like the most exciting topic at first,
Yeah.
but it gets really interesting, I promise.
Okay, you've piqued my curiosity. So
Yeah.
what exactly was Langmuir looking at with these oil films?
He wanted to understand how they behave, how they spread, what they're like at the molecular level.
Molecular level. So we're talking really, really small here.
Exactly. It's all about those tiny, tiny interactions.
Okay. But wasn't he, way ahead of his time with this kind of research?
Not entirely. Actually, scientists like Agnes Pockels and Lord Rayleigh were already experimenting with oil film.
Before Langmuir.
Yeah, even before him. Gosh even mentions Pockels as this unsung hero, the pandemic hero we needed.
Pandemic hero, what do you mean?
Well, think about it. She was stuck at home, right? But that didn't stop her. She found ways to create these water surfaces and study how oil spreads on them.
Wow, that's dedication. But how does she even do that at home?
Well, she used things like tin strips and coins to measure the surface tension.
Tin strips and coins.
Yeah.
Yeah.
She was super resourceful and figured out ways to make it work with what she had.
That's amazing. So what was Langmuir's contribution then? If all this was already happening before he came along?
Well, Langmuir took it to a whole new level. His genius was in looking at something seemingly unrelated, the gas equation.
Wait, the gas equation, as in PV equals nRT.
That's the one. He had this amazing insight. He wondered, what if there's a similar equation to describe how molecules behave on a surface?
Okay, I'm not seeing the connection yet. How do gas molecules and oil films relate?
It's about how things behave when they're confined. Imagine a crowded room, right?
Okay, I can picture that.
As more and more people squeeze in, everyone has to adjust how they're standing, how they move.
Right, it gets kind of awkward.
That's exactly. Langmuir thought the same thing might happen with molecules on a surface. Compress them, and their behavior changes.
So he's saying a surface is like its own little world with its own set of rules for how molecules act.
Precisely. And he even imagined these molecules existing in different states, just like matter in our 3D world, like spread out like a gas, clustered together like a liquid, or tightly packed like a solid.
That's a cool way to think about it. But how did he actually prove this? How do you even see molecules behaving on a surface?
That's where Langmuir's experimental genius comes in. He devised this simple yet ingenious test using talc powder.
Talc powder.
Yeah, the stuff you find in baby powder. He sprinkled it onto the oil film and watched what happened.
Okay, and what did the talc tell him?
If the talc moved freely, it meant the oil film was acting like a liquid with the molecules flowing around.
I see, like it was slippery.
Right, but if the talc stayed put, stuck in place, then it indicated a more solid-like behavior with those molecules locked in a rigid structure.
So by watching the talc, he could actually see the different states of the molecules. That's so clever.
It is, isn't it? Simple yet brilliant. And it gets even better. By carefully measuring the area the film covered and knowing how many molecules were there, he could calculate the area occupied by a single molecule.
Hold on, he could measure the space taken up by a single molecule. That seems impossible.
It might sound incredible, but that's precisely what he achieved. And this is where things get really interesting.
Okay, I'm all ears.
His calculations not only confirmed his ideas about these different states of molecules on a surface,
Right.
but they also revealed something surprising about their orientation.
What do you mean by orientation? Like which way they were facing?
Exactly. It turns out they weren't lying flat on the surface as you might expect. Instead, they were standing upright with their water-loving heads dipped in the water and their water-repelling tails sticking up in the air, almost like tiny buoys bobbing on the surface.
That's an incredible picture. So just from studying these oil films, he was able to figure out how individual molecules were arranged on the surface.
Exactly. And that was just the beginning. He went on to use this understanding to figure out all sorts of things about molecules.
Like what?
Things like their lengths, even their shapes. It's all connected.
Wow, there's so much more to uncover here.
Oh, there definitely is. Are you ready to explore how Langmuir's calculations revealed even more about the molecular world?
Absolutely. Let's dive in. So we left off with Langmuir figuring out that these molecules in the oil films, they can be like a 2D gas or liquid or solid.
Right.
And he could even tell which way they were oriented.
Like tiny buoys, heads down, tails up.
Exactly. But how did he go from there to actually measuring the size and shape of individual molecules?
Yeah.
That seems like a huge leap.
Well, it all comes down to his ability to connect different pieces of the puzzle.
Okay.
He already knew the area a single molecule occupied on the surface, right, from those oil film experiments.
Right, right.
And then he brought in information about the molecule itself.
Like what kind of information?
Things like its density, its molecular weight.
So he's combining those measurements from the oil films with what's known about the molecule itself.
Precisely.
Yeah.
And using Avogadro's number, which tells us how many molecules are in a given amount of substance.
Right.
He could calculate the volume of a single molecule.
Okay. So it's like if you know the total volume of a wall and how many bricks it took to build it, you can figure out the size of a single brick.
Exactly. That's a great analogy.
And then he takes that volume and
divides it by the area the molecule occupies on the surface.
So he's basically using a 2D measurement to unlock a 3D property.
Exactly. It's pretty elegant, isn't it?
It is. So what did he find? Did his calculations match up with what was already known about these molecules?
They did. The length he calculated for each carbon atom in the molecule, it was consistent with what was known about carbon bond lengths.
So he's not only confirming his own ideas, but also supporting existing knowledge about molecular structure.
Exactly. It's a double win. But Langmuir didn't stop there.
Of course not. He never did. What else did he do?
He went on to define something he called the aspect ratio of a molecule, which is essentially a way to describe its shape.
Aspect ratio. I'm not familiar with that term.
Think of it like this. A pencil has a high aspect ratio because it's long and thin, whereas a basketball has a low aspect ratio because it's more round and compact.
I see. So he's saying the shape of a molecule is just as important as its size when it comes to understanding its behavior.
Exactly. And it's all about how they pack together, how they interact with each other.
Like puzzle pieces. You need to know both the size and the shape to make them fit.
Precisely. It's a really important concept.
It is. It's incredible how these seemingly simple experiments with oil films led to such profound insights into the molecular world.
It speaks volumes about Langmuir's genius, doesn't it? He had this remarkable ability to see the bigger picture, to connect the dots between seemingly disparate concepts.
Right. He wasn't just focused on the specifics of one experiment. He was looking for those underlying principles that govern how matter behaves.
Exactly. And that kind of thinking, that willingness to draw analogies, that's often what leads to those aha moments in science.
It's like he was saying, hey, maybe the rules for how gas molecules bounce around in a container can tell us something about how molecules act on the surface. And it turns out he was right.
Exactly. It's a beautiful example of how scientific principles can be applied across different fields, often in unexpected ways.
It makes you wonder, what other connections are we missing? What other seemingly unrelated things could hold the key to new scientific discoveries?
It's a great question, and it brings us back to one of the key takeaways from Langmuir's Nobel Lecture.
Which is?
He emphasized the interconnectedness of scientific disciplines. He argued that there's no fundamental distinction between what we call chemical forces and physical forces.
So he's saying whether we label it chemistry or physics, it's all ultimately the same forces at play.
Exactly. It's just our human way of categorizing things.
That's a really intriguing perspective. So he was advocating for a more holistic view of science.
Absolutely. And his own work is a perfect example of that. He seamlessly blended principles of physics and chemistry to make these groundbreaking discoveries.
And his work continues to influence multiple fields of science today.
Absolutely. But before we wrap up our deep dive into Langmuir's world, I do want to mention something Ghosh pointed out. He found Langmuir's Nobel Lecture itself to be a bit dry.
Oh, that's surprising.
I know, right? But let's be honest, trying to explain these complex scientific concepts in a way that everyone can understand, it's a real challenge.
It is. It's a delicate balance between being accurate and engaging.
Exactly. And sometimes the subject matter itself is just inherently complex.
I could see that. But even if the lecture itself wasn't the most exciting read, there's no denying the impact of his work.
Absolutely. He truly revolutionized our understanding of surfaces and molecular behavior.
And his legacy continues to inspire scientists today. He set a high bar for scientific rigor, for ingenuity, for that pursuit of fundamental understanding.
He did indeed. But before we move on, I want to touch on something we haven't really talked about yet.
Okay.
We focus a lot on Langmuir's research, his insights,
Yeah.
but what about the man himself? What kind of person was Irving Langmuir?
You know, it's amazing to think about how someone experimenting with oil films, almost a century ago, could have such a huge impact on fields like, material science and nanotechnology today.
It's true, isn't it? Langmuir wasn't thinking about those applications back then.
Right.
He was just driven by that curiosity, wanting to understand those basic principles, at a molecular level.
Right.
And that's what led to those truly groundbreaking discoveries.
It's like he was laying the groundwork for entire fields of science that didn't even exist yet.
Yeah, exactly.
So what are some specific ways Langmuir's work is still relevant today?
Well, think about material science, for example.
Right.
Understanding how those molecules arrange themselves on surfaces, it's crucial for developing new materials, with specific properties.
Right.
Like, do you want a material that's water repellent?
Right.
Or one that's incredibly strong?
Yeah.
It all starts with understanding those molecular interactions at the surface.
So something as simple as an oil film can help us design these cutting-edge materials.
It can. It's pretty amazing, right?
Yeah. It is. It really shows you how fundamental research, it can have these ripple effects across time.
Absolutely.
It's not always about those immediate applications.
Right.
It's about building that foundation of knowledge.
Exactly. And sometimes it's those seemingly unrelated discoveries that end up being the key
Right.
to solving these bigger puzzles down the line. Langmuir's work, it really highlights that.
It does. That importance of curiosity, perseverance, that willingness to look for connections.
Exactly. He saw those patterns, those possibilities where others didn't. And his legacy, it really encourages us to think outside the box, challenge those assumptions.
To push the boundaries of what we know.
Precisely. He showed us that science is not just about memorizing facts or conducting experiments. It's about embracing that mindset of curiosity.
It's creativity.
Yeah. And a deep desire to understand those fundamental workings of the universe.
Absolutely. And, as we wrap up our deep dive into Langmuir's world,
Yeah.
I'm left with this feeling that he wasn't just this brilliant scientist. He was a reminder that science, this journey of discovery,
It is.
driven by that human curiosity and that pursuit of knowledge.
Exactly.
And even though we've reached the end of our exploration today,
Yeah.
I have a feeling his story will continue to inspire us to look at the world with a sense of wonder and never stop asking why.
I think you're absolutely right. And who knows, maybe one of our listeners, inspired by Langmuir's story, will make the next groundbreaking discovery.
You never know.
The potential is all around us.
It is. Well, on that note, I think it's time for us to say goodbye.
Yes!
Thank you for joining us on this deep dive into the life and work of Irving Langmuir.
It's been a pleasure.
It has been an absolute pleasure exploring his world with you.
Likewise. Until next time.